Hi students, a very good evening. Welcome to JEE Amrita crash course. I hope everybody is doing good. Right, good evening all. So if there is any audio issue or video issue, please let us know. If it is clear, please say yes. Is it clear? Audio, video? You're able to see the screen properly, right? Okay, audio is fine. Okay, thank you. Okay, so now we can proceed. So today also we are going to discuss some very interesting concepts in chemistry. Okay, I hope you will learn more new concepts and more exciting concepts today with beautiful questions. Shall we start now? Okay, fine. We'll start. So first question here is this question based on crystal systems. Okay, do you know in the whole universe, no, whatever may be the crystal, we can classify them into seven of the crystal systems. Means whatever may be the crystal we find here. One second. Okay, so in the whole universe, whatever may be the crystal, it is one of the types of seven crystal systems. Okay, three-dimensional crystal systems. So what are they and how do we remember these seven crystal systems? I'll give you a very simple trick. Okay, very simple trick. So please look at this. So there are seven crystal systems. I'm giving you very simple trick now. How to remember these seven crystal systems? Because in seven crystal systems, we should know ABC. ABC means what? See, look at 3D. Okay, this is x-axis here. Okay, second. This is x-axis and this is y-axis. This is z-axis. We should know what is the length along x-axis. Okay, so this is A. What is the length along y-axis? This is B. Same length along z-axis is C. And see this A opposite angle. Always A opposite angle is alpha, B opposite angle is beta, C opposite angle is gamma. That means we should know the distances, the lengths along XYZ axis and also the angles between the axes. See, look at this CT or HMT. So this is our trick to remember seven crystal systems. So we have CT or HMT. Sir, what is CT or HMT? So one by one, okay, now we'll decode this. So this C for no cubic system. Okay, cubic system. T for tetragonal system. Okay, O orthorhombic system. Okay, R means what? Tell me, R means rhombohedral. Yes or no? Rhombohedral system. Okay, next H hexagonal system. Monoclinic. Okay, last one is triclinic. So this is a trick, no, we use in the systematic way. We have written this CT or HMT is our trick. Okay, so what is the trick here? So here very simple, orthorhombic is given, fine, but if any crystal system is given, we should be able to find out ABC and alpha beta gamma relation easily. So after this class, no, after this trick, you will be easily able to identify, no, any crystal system very easily. So first cubic system ABC relation I'm writing here, A equal to B equal to C. Okay, A, B, C. Now this A is B not equal to C. 1 is cancelled. Okay. A is B equal to C, but B not equal to C. And next, no, orthorhombic, A not equal to B not equal to C. And these three I have written, right? CTO I have written. So next, no, you repeat these three again. You repeat this three means, see this three like a triplet, no? Consider like a triplet. You repeat this again. Okay. The systematic way, A equal to B equal to C, B not equal to C, A not equal to B not equal to C. Triplet is done, right? So the six crystal systems are covered. No, next one is again, no, triclinic is very simple. A not equal to B not equal to C. And what about this alpha beta gamma relation? These are lengths, right? For 7 crystal systems, the lengths, relation between lengths are this. Okay, isn't this simple? Yes, right? Lengths. Now angles, coming back to angles, alpha, beta, gamma, 90. They are all equal to 90. And see this also same. Very simple. Now what about orthorhombic? Orthorhombic again same. Again triplet is coming. Very simple. All angles are equal and they're equal to 90 degree. But look at this rhombohedral. Rhombohedral, they are all equal, no doubt, no. But angle is not 90. Okay, alpha, beta, gamma are equal. That can be 60 degree, that can be 90 degree. But all of them are equal, but not equal to 90 degree. Okay, right. Next, hexagonal is little bit different. Alpha, beta 90. Okay, but see gamma is 120. This is hexagonal. Now monoclinic is alpha, gamma 90. Okay, but beta is not 90. Any means it is not 90 degree, any angle other than 90 degree. Now last one is again very simple. Alpha not equal to beta not equal to gamma not equal to 90. They are not equal and not equal to 90 also. So only these, no, in angle cases H and M are difficult. Means for memorizing it is difficult, but rest all are very simple. So this is a trick. I hope everybody liked it, right? CT or HMT. You can do this on fingertips now, right? CT or HMT. And look at triplet here, right side, no? ABC relation. Okay, just close your eyes, no? You should visualize this. Okay, 7 crystal systems. So proper trick, no? ABC, alpha, beta, gamma. Got it? Fine. Now see this, no? Which is matching orthorhombic. So without any doubt, A not equal to B not equal to C. Yes. Alpha, beta, gamma is how much? CTO, right? Option B. Exactly. No, this is option B. Got it, right? So this is a question from solid state, and it's a basic question. Okay, 7 crystal systems on your fingertips. Okay, right. We'll move on to the next question. Okay, right. Look at this. This question is asking FCC crystal contains how many atoms in each unit cell? There is FCC, but what is FCC? Okay, let me elaborate this. No, FCC means what? You tell me. I'm checking the chat box. No, just tell me what is FCC. Face centered cube. Very good. Okay, face centered cube. Okay, face centered cube. Look at this carefully. Look at the name, no? Face centered cube. What does that mean? That means you draw a simple cube. Okay, there's a simple cube. Okay, the simple cube, and look at this carefully. The simple cube means A equal to B equal to C. Length, breadth, height, everything is same. No, all are equal to A. That is what the meaning of simple cube. Okay, face centered cube means what? Where are the particles? So look at this particles, corner particles, no? So this dot is not the atom. Basically, listen carefully, this dot is not the atom. This dot indicates position of atom, lattice point. We say this lattice point, very very important. While keeping this dot in solid state means what? This dot is lattice point. Okay, I'll write it. Okay, dots are lattice points. Lattice point gives no position of particles. It is not the atom only, it can be any particle. It can be atom, it can be molecule, it can be ion. No, position of particle, it just represent position. And don't imagine like this dot is particle. No, no. This is particle position, right? Now next, face center, right? Face center means what? Now there are how many corners for this cube? 8 corners. Okay, now tell me quickly, if there are 8 corners, no, 8 corners, how many faces are there for cube? Everyone should respond now. How many faces for cube? For a cube, 6 faces, exactly 6 faces. Okay, how many edges are there? How many edges? Edges means this, no, this lines. How many lines are there? How many lines you are able to see? 12 edges. No, 12 edges. Okay, edges are 12, faces are 6, 8 corners. Fine. One more important thing, how many body diagonals? How many body diagonals? Different body diagonals. That means, see, if you are sitting in a room, okay, is it like a hall or your study room? No, just imagine room like a cube. Imagine room like a cube. No, this, you are sitting in a cube. Okay, now just visualize, no, imaginary lines. How many body diagonals from corner to opposite corner? How many body diagonals will be there? Exactly 4. Okay, 8 corners are there, just connect opposite corners. No, so what you will get? 4 body diagonals. So this information is must, everybody must know in solid state. Okay, now if there is any atom, if there is any atom at the corner in 3D, okay, what is its contribution? Corner contribution is how much? Corner contribution, if you place any atom now. Okay, now face center means I'll draw where I'm placing your face center, right? So this is face center, this is face center, this is face center. So 4 face centers are over, right? Now front and back, no, I'm writing here, this is front, okay, and this is back. Very difficult to represent because in 3D diagram writing on plane of paper is little bit tricky and difficult. No? Corner contribution is how much? It can share with other 8 such unit cells. But what is unit cell? This is the smallest part. If you repeat in different directions, no, up, down, okay, front, back, left, right, this will give entire structure of crystal. Okay, corner contribution is 1/8. Okay, face contribution, you can imagine, no, I told you, right? If you're sitting in a room, just imagine, no, all those walls are faces, and edges you can properly visualize, corners you can properly visualize. From that you can construct a beautiful unit cell. Okay, face contribution is 1/2. Okay, edge contribution is 1/4. It is maximum common to 4 such unit cells. Okay. Now our unit cell is FCC. FCC crystal. Coming back to this question now. FCC crystal. How many atoms in each unit cell now? Corners. No? Number of atoms. Look at this. Number of atoms per unit cell. You can see there are 8 dots. Okay. 8 dots plus 8 red dots plus 6 green dots. 14 are positions. Okay, but if you place atom there, no, it is not belong to that particular unit cell only, it can be shared. That's why I mentioned these dots are lattice points, no? If you place any particle there, that is common for other unit cells also. So that is what we did here, corner contribution. If you place atom, molecule, any particle at corner, that is common to 8 other unit cells. So now if you see this, we have corner atoms, 8 corners, 8 red dots, but the contribution is just 1/8 part only. Each corner atom, just 1/8 part belong to this particular unit cell. And this green dot is phase center. There are 6 phase centers, but 1/2 part, 1/2, half part belong to this. Okay, so this is 4. So this is how you should visualize. Okay, and uh, the structure, diamond structure. Anybody knows what is diamond structure look like? Diamond, carbon allotrope diamond. Do you know what is it? How the structure will, it's solid state structure. Sir, we know graphite is like a layer structure, layers distance also we know, and carbon atom distance, fine, no? But diamond crystal solid state structure, so I'll tell you. Okay, diamond structure, very important. So this is one of the best example for FCC. Okay, diamond, carbon atoms. Okay, carbon atoms, only carbon atoms are in FCC. Okay, so that means every corner is occupied by carbon atoms. Yes, tetrahedral geometry, no, tetrahedral shape, sp3 hybridization, yes, that is fine. But solid state structure, I'm not asking molecular geometry, no, solid state structure. In solid state, okay, how carbon atoms are arranged. So carbon atoms are in FCC, and also alternate tetrahedral voids. We'll discuss now. Okay, tetrahedral voids. What is tetrahedral void means? Because when you place the atoms in 3D, there are some spaces created because atoms are rigid, assumed as rigid spheres. Okay, for a simple calculation purpose, what we do is, see, if you place atoms like this, okay, this 3 atoms I placed, circles, rigid spheres, no, and one atom I'm placing above this. One atom I'm placing above this. Now look at the space created, no, between those 3 blue ones, no, between these 3 blue circles, they're actually spheres in 3D. Okay, that space is touching with how many spheres? So the red one is from the top layer. Okay, you have to visualize like 3D, right? So 3 atoms on first layer. Okay, there is space created. So this is blue one is layer 1, red one is second layer. We're placing atoms above this. Now this space is touching with, touching with 4 atoms, 4 circles, right? Or 4 spheres in 3D. Exactly, right? So that creates tetrahedral void. So carbon atoms are in FCC and also alternate tetrahedral voids. So that is diamond structure. Best example for FCC. Okay, fine. Now look at this question. A compound formed by a cation C, and anion A. Now anions forms HCP lattice and cations occupy 75% voids. I just explained this is a void, tetrahedral void. So like that, there is octahedral void also, no? Look at this, no? I'll show you octahedral void. See, this is octahedral void. Draw this 3, okay? And see this other 3. You should understand what are voids. Voids are just empty spaces. But based on their neighbors, no, we are dividing into 2 types. Basically, in 3D, we get 2 types of voids, tetrahedral and octahedral. And we have a simple calculation also for numerical purpose. Number of tetrahedral voids is equal to 2 into n. What is n here? N is number of atoms per unit cell. If n atoms are present, tetrahedral voids are 2n, and number of octahedral voids are n only. Okay, fine. Now look at this question now. It will be easy now. So HCP, okay, anions forms HCP. How many atoms per unit cell now? If it is HCP, slightly different, right? It is not FCC. HCP, number of atoms per unit cell. Number of atoms per unit cell is 6. It is not 4. No, it is not FCC. It is 6. Okay, HCP is 6. Number of what atoms here? Number of anions, right? A ions. So number of atoms per unit cell is 6. So A atoms. I'm writing A. Okay. How many C should be there? It is based on voids, right? Octahedral voids now. Number of octahedral voids. How many should be there? So we just now discussed this, right? If there are 6 atoms, if there are 6 atoms, there are 6 octahedral voids. So there are 6 octahedral voids, no doubt. But 6 are not occupied, no? 6 are not occupied. Okay. 6 are not occupied. How much percentage is occupied? 75% is occupied. So number of A6, number of C is equal to 3/4, right? Into 6. 3/4 into 6. So how much it is? 3/4 into 6 means this is 3 times, this is 2 times, this is 9/4. 9/2, sorry. 9/2. Okay, fine. Now A we know, okay, and C. C is 9/2. We'll write it like this. C is 9/2. A is 6. So we'll convert into simple ratio. Multiply with 2. C 9, A 12. Our simple ratio will be 3 times. This is 4 times C3A4. So this is how you should do it. Okay. If you are able to understand the concept, you can do n number of questions easily. If you get the concept properly. If you know number of tetrahedral voids are 2n, octahedral voids are n, whatever may be the percentage given, you should be able to calculate this way. Okay, done. So what is our answer now? C3A4. Correct, C3A4. So we'll move on to the next question now. I hope everybody understood, right? Tetrahedral void, octahedral void. You got the clarity. Okay, option D. Very good. Done. Next question. See this. FCC we have done. See, different models we are doing here. FCC we have done. HCP we have done. Now BCC. Now BCC. Okay. BCC, if you look at, an element has body-centered cube structure with a cell edge of 288 pm, no? Picometer. 1 picometer is how many meter? 10 power. How much? Do you know? 1 picometer is how many meters? Do you know this? Picometer. 10 power minus 12 meter. Okay. 10 power minus 12 meter. That is 1 picometer. Or directly you can write no 10 power minus 10 centimeter. Okay, fine. So that is just unit conversion. Now look at BCC. What is BCC? This BCC, if I draw here, body centered cube. Corners, obviously there is particle. Okay. Corner has particles and also the center of body. Okay. Corners and also the center of body. Okay, body center. So look at this, no? They're asking about distance. And if I place a particle, no? If I place a particle at red and a particle at green, okay? So what is this distance here? I'll draw with different line, okay? What is the distance here? Do you know? It is exactly half of body diagonal. Exactly, right? Half of body diagonal. So what I can write is, this is just like this, no? One atom is touching with an atom. So that means if you draw atom, so what I'll do, I'll draw an atom, okay? This is an atom, okay? This is an atom, and this is again atom at the center, okay? This is means identical atoms, okay? Identical atoms. So this you can write, no? 2r, both are touching. 2r is equal to root 3a by 2, half of body diagonal. Exactly. Okay. Now what is the radius here? Root 3a by 4, right? Root 3a by 4 is this, no? A is given, just substitute. Got it? So that means we should know position of atoms. Okay. Right. Next. This is interesting question. See this. Iron exhibits BCC structure. We know what is BCC and we also know what is FCC. The ratio of density of iron at room temperature to that at 900 degrees Celsius. So what it is saying is, at room temperature, iron is BCC. Look at this carefully. Iron, okay, it is BCC structure, but the crystal structure is getting changed when, if you heat it 900 degrees Celsius, sorry, iron getting changed to FCC. Same element. Okay. Now ratio of density of irons, room temperature, let us say this is room temperature, right? This is at room temperature and this is RT I'm writing, and this is at 900 degrees Celsius. Okay. So I'm taking this density is D1, this density is D2. Okay. So what is the ratio of D1 by D2? Assume molar mass is same. Yes, no doubt. Molar mass of iron is not getting changed, right? If you heat iron, is there a change in mass? Molar mass? No. Per 1 mole it is same, right? And atomic radius? Yes, it is also, we are assuming it is same. Atom, right? Atom is not extended. Atom is not compressed. Atom is not compressed. Okay. So atomic radius is same, molar mass is same. Then what is the ratio of density? How do we do this? What is density formula? First we should know, right? What is density? D1 by D2 they are asking. Yes, no? Fine. See this carefully. D1 by D2 is how much? What exactly density means? Density is equal to mass by volume, right? Yes, mass by volume. So mass means mass of total atoms. No, I'm writing Z into M by A cube into Na. Sure. What exactly is this? See, look at this carefully. M is molar mass. Na, Avogadro number. So what I did is total mass by volume. A cube is volume, right? So instead of simple mass of one molecule, what I did, molar mass I'm writing, I'm multiplying with Na. Okay, fine. This is D, density. So density D1 is equal to how much? For BCC, how many atoms per unit cell? Tell me. Initially BCC, right? Tell me how many atoms? 2 atoms. Yes, exactly 2. Yes, I'll write 2. Molar mass we kept constant. Yes. So they are saying atomic radius is constant. Exactly, atomic radius. Now, what is the relation just now we discussed? No, BCC equal to 4 R equal to root 3 by 4, right? What is A is equal to? A is equal to 4R by root 3. Yes or no? A is equal to 4R by root 3. So what I'll do, I'll substitute this. They are saying R is constant, right? Not A. Edge length can be changed. Okay. 4r by root 3. Okay, Na. Done. Okay, option C. Okay, right, let us see this, 4r by root 3 Na. Now D2. Now D2 is what? D2 is FCC. FCC, tell me how many number of atoms per unit cell. This also we did, right? We discussed a systematic way, BCC, FCC, HCP, FCC. Okay, so that is 4 into M by, this is 4R by, how much it is? It is FCC. 4R by root 2 or root 3. It is phase diagonal, right? Phase diagonal is root 2a. So this is root 2. And that is whole cube, no? Achha, don't forget this, whole cube. Don't forget this, okay? Whole cube into Na. Now we can calculate, right? D1 by D2. Okay, so D1 by D2. So 2m by 4r cube. This will get cancelled anyway. And this will be 3 root 3. Okay, 3 root 3 into Na. And this will be D1 by D2, right? So what I'll write is, this is 4r whole cube by D1 by D2, right? Okay. 4r whole cube by 2 root 2, okay, into Na. So by 4m, right? This way, right? R is constant, we said. Yes, this is getting cancelled. Na gets cancelled, right? 2 cancel. 4r cube gets cancelled. Okay, so now what is remaining here? 3 root 3. Achha, this 4 is left here. Okay, 3 and root 2 and root 3. So what is the correct answer now? 4 comes to the numerator. Yes, 4 comes to the numerator. Okay, 4 by this root 3 also comes to numerator, right? 4 comes to the numerator. Is it so? 4 is 4r cube root 3 whole cube 3 root 3. Acha, how root 2 came? Acha, just simple mathematics. Yes, fine. See, look at this, how root 2 came. I'll explain this. After this is very simple maths, I know. See, it is FCC, right? It is FCC. And look at this. If it is FCC, look at the atom position. Look at atom position. And here there are atoms, no? Phase, position I'm representing, and there is atom here. Now look at this. There is atom here and red color corner atom, and the distance between them, the distance between these two, no? This is 2r is equal to, what is phase diagonal? Phase diagonal is root 2a by 2. So this way we get, no? R is equal to root 2a by 4. So what is our final answer? You calculated, right? Okay, fine. What is the final answer? C, you are getting option. Okay, done. The rest calculation you do this, no? I clearly done till here. You can do that. Sorry. Okay, fine. Next question. Right, now also very important question here. Right. Formula of nickel oxide with metal deficiency defect in the crystal is Ni 0.98 oxygen. The crystal contains Ni plus 2 and Ni plus 3 ions. Fraction of nickel existing as Ni plus 2. See, this is weird, right? Ni, generally compounds are how the formula will be MO2 or M2O3. Okay, but we don't get fractions normally, right? We don't get M.6, no? M.6 oxygen or M.9. But this is possible when there are transition elements. It is not possible with, see, you don't find like sodium 1.5 oxygen. No, you don't find this. Or sodium 0.5 oxygen. No, you don't find. Only in transition metal what happens, because of vacancies, no, oxygen or hydrogen or nitrogen, they get trapped. Okay, so that is why we get this. But sir, but what is the meaning of this? Is it fraction of atom? No, 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 not like that. See, you will get to know, just multiply with 100. Okay, multiply both atoms with 100. 9 nickel 98, oxygen 100, right? If you multiply, so what is the meaning here? The meaning is not the fraction of atom. Instead, 100 atoms of oxygens are trapped in 98 nickel atoms. Okay, between 98 nickel atoms, 100 oxygen atoms are trapped. But you can't say 0.98 atom. No? Atom cannot be fraction. No. So this is the meaning of non-stoichiometric compound. Okay, right. So now look at this. But Ni can be in two different states, Ni plus 2, Ni plus 3 to say. So what you can write is, you can use this. Okay, so there are 98 atoms. So I'm clearly taking here, let us say X atoms out of 98, Ni are plus 2 state. We need to plus 2, right? We need plus 2. Okay, out of 98, X atoms are plus 2. So then 98 minus X atoms of nickel, no, they carry plus 3 state, no doubt, right? Total atoms are 98. I'm just taking X atoms are plus 2 state. So 98 minus X. Okay, 98 minus X atoms are plus 3 state. Fine. Oxygen charge. What is oxygen charge? In oxides, what is oxygen charge? Suppose sodium oxide, magnesium oxide. What is oxygen charge? It is, can anybody tell me what is oxygen charge? Minus 2. Exactly. Okay, it is minus 2. So look at this. X atoms carries plus 2 charge. So total charge must be equal to 0 because it is neutral, right? Total charge on this Ni 98, oxygen 100 is 0. So let me write properly. X into plus 2. X atoms charge plus 2, right? So total charge will be X into plus 2 plus 98 minus X. 98 minus X into plus 3. This is nickel. Plus oxygen is minus 2 charge into 100 atoms, that is equal to 0. Okay, so 2x plus 98 into 3, okay, minus 3x plus minus 200 is equal to 0. So we'll get x, right? Minus 3x plus 2x. So 98 into 3, how much? Just calculate this quickly and find out what option we get. 98 into 3, 294, right? 294 minus 200 is 94. X equal to 94. So fraction is how much? X is what? Atoms of 9 atoms with plus 2 state, but they're asking fraction, right? So the fraction is, fraction of atoms is equal to 94 by 98. Out of 98, 94, right? So what is the answer now? You can clearly eliminate the options, right? 94 by 98, no, it can't be this, right? It can't be BCD, no. It is more than 95%, right? 94 by 98. So it is 0.96. Okay. Understood? We have done here very simple mathematics. No, total charge must be 0. Whatever may be the amount of nickel atoms, no, whether they can be plus 2, they can be plus 3 state, but the total charge must be 0. Got it? So fraction is 0.96. You can easily eliminate the option also. Fine. Now, one more interesting question here. If NaCl is doped with 10 power minus 4 mole percentage SrCl2, concentration of cationic vacancies. What does that mean? Doping means what? Do you know what is doping? Anybody knows here what is doping? Doping means addition of impurity. Yes. Okay. Yes, adding impurity is doping. Exactly. So we are adding an impurity SrCl2. Okay, and look at this. There is, if you add impurity SrCl2 impurity, how does it make differences, vacancies? No. So what you should remember is, in solid state, in ionic solids, basically in ionic solids, you must know charges get balanced, whether you get 0.9 no or 0.5, like last example, the charges must be balanced. Okay, plus overall it should be neutral. So you have to keep in mind that. Okay, minus plus, minus plus. Okay, and there is plus minus. In NaCl, atoms, ions are arranged like this, right? Sorry, 1 second. Every plus should be with minus. Okay, there is minus and there is plus and there is again minus. Okay, so there is plus, there is minus, there is plus, like this. Now if you see, this is ideal NaCl crystal, but we are doping it. If you dope it, no, Na charge is +1, Cl charge is -1, but Sr is +2, but still Cl is minus. Okay, so Cl minus doesn't make any difference, but Sr +2 can make difference. How it makes difference? See this. I'm removing, no, because the charge is 1 here, +1 here, but the charge is +2. If I need to replace sodium with Sr+2, what I should do? I should remove, no. So there are two Sr, 2 Na plus. Look at this. I remove this. I remove this. Now I will add +2 charge. I will add +2 charge. See this? I'll highlight this with another color. Okay. Okay, done. So this will be +2. I placed one +2. So no need to add this. This will be left vacant because +1 I removed. 2 Na plus I removed. 2 Na plus I removed. But I doped with SrCl2, right? So Cl minus doesn't make any difference, right? Cl minus position is fine. But Sr+2 makes difference, right? So if there is one Sr+2, let us say this is Sr+2. Okay. And how many vacancies are there here? There is one vacancy. One vacancy. Okay. So what I can say is, number of Sr+2 is equal to number of, this must be cation, right? It has to be cation because we removed 2 plus charges and we replaced 1 plus 2. So number of cationic vacancies. Okay. So now it is very simple problem, right? So how many vacancies here? 10 power minus 4 mole percentage. So number of cationic vacancies are simply cationic vacancies. I can write 10 power minus 4 mole percentage into Avogadro number 6.023. You can write this also. 10 power minus 4 mole percentage. So what is the correct answer now? So this is 6.023 into 10 power 23, this one, and 10 power minus 6, no? So 10 power 17. So option B. Getting the point, right? Understood? Yes, exactly B. What we are doing here, remove 2 plus charges, plus 1 charges, and replace 1 plus with +2. So charge gets balanced, no? What we did, we removed 2 plus 1 charges, 2 Na plus, and that is replaced with an Sr+2. So very simple how we should do this is so 2 plus charges I removed. Okay, 2 plus charges I removed, but I kept no to balance the charge. I kept 1 plus 2, so that one position is left vacant, right? One cation position is as it is, right? I removed 2 plus 1 charges from the respective position, but one of the position I kept plus 2 charge. Okay. Understood, no? Okay, done. Right. Next question. Look at this simple question now. This is from solutions. Okay. Molarity of H2SO4 solution that has density and contains 98% by weight. Molarity directly. Density is given gram per centimeter cube and mass percentage. I'll tell you one simple formula. If you want, you can remember this. Okay. Without this formula also you can work out. Weight percent, okay, into 10 into density by molecular mass. So this is best way to calculate molarity if you know weight percent and density is given. This is very simple. Okay, direct formula. So weight percentage 98 directly, and don't write 0.98. Don't write 98% sir, 98 by 100. Don't write this. We already did this. No, weight percentage we should take. I have written here weight percentage into 10 into density 1.84 by molecular mass of H2SO4 is 98 again. 18.4. Okay, 98 gets cancelled. 10 into 1.84. Sir, if I don't know the formula, sir, if I forget this formula, how do I proceed? No, M is equal to N by V. This we must know. V must be in liter. So if you take V in ml, no, in 2000, we must know this. Okay. Now 98% by weight. Okay, by weight, not weight by volume, by weight. So what I'll do is, so very simple way, like normal way, without knowing any formula. Suppose I don't know this weight percentage into density. I don't know this formula. Okay. So what I'll do, 98% is given. So I'll proceed like this. 98 gram. Percentage by weight means 98 gram H2SO4 present in 100 gram. Percentage means what? Per 100, right? 100 gram solution. 100 gram solution. Okay. So what we know, 98 gram H2SO4 and in 100 mass is given and density is given. How to get volume? 100 by 1.84 ml solution. Yes, we created volume. Now it is very simple, right? Now you can substitute. 98 grams. No, how many moles it is? Molarity. I'm writing 1 mole. Yes. Okay. By volume is 100 by 1.84 into 1000. So you'll get the same answer, right? Either this way you can proceed. Okay. Or this way. I did very simple maths here. 98 gram H2SO4. We should know what is percentage. Percentage is always per 100. Percentage, right? Per 100 gram, 98 gram H2SO4. Yes. And I converted mass into volume. Okay. Understood? You can take any method, no? Either first or second method. Try this question, no? Vapor pressure of two liquids P and Q are 80 and 60 torr respectively. What is total vapor pressure of solution obtained by mixing? See, this is Raoult's law. What is Raoult's law here? P is equal to PA plus PB. Total pressure. Raoult's law applicable for liquids. Dalton's law applicable for gases. In states of matter, you might have studied Dalton's law. It's the same. P equal to Pa plus Pb. If you mix two gases, total pressure equal to sum of those two pressures. Even in case of liquids, this is called Raoult's law. Fine. So this P is equal to mole fraction into P naught A plus mole fraction into P naught B. What is mole fraction of A? Mole fraction means respective moles, no? So P, okay, and Q, like A and B I'm taking, no? Vapor pressure of pure liquids 80 and 60. This is given, okay, 80 and 60. So what I'll do, mole fraction of P. So mole fraction of P, 3 moles and 2 moles. So 3 by 5, okay, P naught A, it is how much? 80 torr plus mole fraction of B, 2 by 5 and into this is 60. Okay, so what is the answer here? What is the correct option? 72 torr. Are you getting this? Okay, so calculation, you can do it. Understood, right? Very simple. Mole fraction into its pure pressure. Exactly. Okay, understood. Very simple substitution. Now next question. Next question is just a conceptual question. If it is ideal solution, which is correct? Ideal solution, ideal gas. Okay, ideal gas never exists. Even ideal solution, close to ideal solution is possible, but you don't find any ideal solution. But we study this in chemistry, surprisingly. Okay, there is no ideal person in the universe, but we study. There are some good habits, bad habits. But see, in ideal solution, what we can expect here? Correct option. See, listen carefully. When you mix two liquids, when you mix two liquids, and see, it is spontaneous mixing of two liquids. Delta G mixing less than 0 and delta S mixing should be greater than 0. Entropy should be more than 0, positive, but Gibbs energy should be negative. Okay, and delta V mixing, it should be always equal to 0. But what is this? We'll get 0 volume or what? No, that is not the meaning. Delta V mixing means if I add 5 ml of A plus 5 ml of B liquid, so I will get 10 ml, not more than 10, not less than 10. That is the meaning. Delta V mixing means it doesn't become 0. 5 ml, 5 ml if I mix, it doesn't become 0. Liquid doesn't disappear, it is against to law of conservation of mass, right? It doesn't disappear. But what is happening here? You are adding 5 plus 5. You are adding this 5 plus 5. You should get 10 ml, not more than 10. It cannot be 10.1. It cannot be 10.2 like that. It can't be 9.8, 9.9. No, so that is ideal solution. Okay. So this is not correct. This is not correct. This is not correct. And see this last option. Delta H mixing is 0. Okay, so what is the meaning of that? No energy, no heat is supplied. In ideal case, no heat is liberated. Delta H is not positive, not negative. It is equal to 0. There is no heat change. Okay, if you mix A and B, you're not observed any heat changes. Okay, and you can do this question later. What is this question? Yes. No? A solution of sucrose. I'll tell you the formula. Very simple. Freezing point will be depressed if you add any solute, non-volatile solute, that is called colligative property. And the formula we use is this, delta TF is equal to want a factor into KF into M. Just substitute the values. So delta TF we need to find out. Okay, I is equal to 1 because it is sucrose, it is not dissociated or not associated. So KF is given. KF is 1.86 And molarity they are saying, no, see, how do you substitute? See, delta TF is equal to 1 into 1.86. Molarity means number of moles per kg of solvent. How many moles are there? Sucrose moles, mass is given by molar mass also given. These many moles. How many kg of water? 1 kg. So we should calculate this. That's it. So we'll get depression. From 0, how much decrease? If you add minus, you'll get the answer. So what is our answer now? Can anybody tell me quickly? So what is the answer? 1.86 into this factor. So do we get this? This you should get, no, 0.372. So freezing point is equal to, freezing point of solution is equal to minus 0.372. That much decrease is there. Delta means compared to 0, so that much decrease is there. So 0 point, don't write option C. Option C is not correct. Okay, it should be A. Okay, compared to 0, it is decreased. So that means when you add any salt or any non-volatile solute, water freezing point will decrease. No, this concept is used in many cold countries. So what they do, they spend lot of money. In India, we are lucky, right? We don't have that much snowfall in all states. Very few states there is snowfall. Okay, but in Canada, like country, in UK, okay, in Russia, no, so there's so much snowfall, so that blocks transportation completely, that blocks the roads. So what they'll do, they add, no, raw salt. Okay, if they add raw salt, what will happen? Water will not freeze easily. It depends on the how much amount you are adding raw salt. More the amount you add, so water will easily convert into liquid part, and that clears the road. Okay, so that's how we can use this concept, no, depression and freezing point. And even the vehicles, the radiators, no, it should have liquid water. If it is ice, if you add it, that is pointless, no, it will not work, it will stop working. So they add non-volatile solutes to it to decrease the freezing point of water. Water should not freeze. Okay, fine. I hope you have learned a lot of new concepts in this session. Okay, so we are ending this session with this question now. So we'll learn more concepts in the next class. I hope everyone enjoyed this class. Yes, so thank you so much. So we'll meet in the next class. Okay, and please share your feedback. Okay, thank you everyone. Thank you.